the DART mission was the first interplanetary defense mission that NASA created in order to see if we can use physics, right? It's that old, it's the classic math problem, the physics problem of you have one thing moving in one direction, this is the asteroid Dimorphos, and then you have a spacecraft with a certain amount of mass coming at it, and what they were trying to do was change the orbit so that the DART mission would impact Dimorphos and slow that orbit down, and we would be able to observe that change over time. Now, I think myself, like most people who are watching this mission, didn't even realize the scale of content and visualization and opportunities to see this thing happen in space from multiple different angles. I don't think we all realized how great this mission was going to be, and it's a real. It's just goes to show you that there are a lot of different programs that NASA does, and the planetary science program is top notch. I think they learned the lesson from the Voyager missions that having a camera on board, and that doesn't mean that every mission has, but we've seen a lot of great things, whether it's Cassini at Saturn, Juno now here at Jupiter. It just took the closest flyby of Europa recently. So there's a lot of really exciting stuff, and this DART mission did not upset or disappoint. So we saw the video of the DART mission impacting Dimorphos. Very, very cool. That red screen at the end when it impacts, the red didn't look like it was like death or anything, but it was finality is what it meant for me, and just confirmation of impact. And that thing was moving so fast. I think it's roughly 17,000 miles per hour that it was going into that asteroid. And the impact that we saw from the LICIAcube sat, which was a tiny CubeSat that was spring-loaded and released out of the back of the spacecraft about 15 days, 2 weeks basically, before the impact. So it was able to take that same momentum and follow behind and do a flyby of Dimorphos and watch the impact as it happened. And it's a really insane view. And there was so much debris that happened. We even got to have a view from the Hubble Space Telescope and from James Webb Space Telescope to get an idea of the impact and what it did. And there was even another one, the Atlas project took a view of it as well, which was the first one that I saw even before the LICIAcube video came out. But so many really, really cool things. And the LICIAcube itself is a great story, right? Italy's space program, this is their first deep space mission. They were completely in charge of this. It was a big day, and they are still potentially able to operate that CubeSat. There's a chance that even though this was a flyby, if there's enough fuel on board and enough energy, they actually empower. They should try and make a second attempt and change the orbit to come back again to take a look at the asteroid impact after the fact. So that's very, very exciting, and it's cool to see that a mission like this is really important because we all have our ideas and our theories and our hypotheses of what is going to happen. And one of the things that I thought was really interesting was, especially if you look at the NASA simulation of what they expected to happen, you see the DART impact Dimorphos, and you can see that they're expecting this symmetric, conical debris release from the impact. So the spacecraft comes in, hits the surface, and then the dust, like a droplet of water, it's going to release like this ring of debris out from the side. And from the research and the expectations that we all had going into what this was going to look like, you look at that animation and you say, oh yeah, all the debris goes out because there's no gravity. It just kind of floats out there into infinity. And what's fascinating is when you look at the images from the LICIAcube, you can see that the debris is gathering in these like spindles or filaments as they're called. And that, from a planetary science perspective, was new information and knowledge that we did not have before watching this mission and actually seeing what it's like in real life, not just theoretical, not just in the lab of what we think could happen by estimating and predicting. We actually saw what it looks like and what it does, and now we can learn more about reality. And so the question is, what forces are at play? What is causing this type of gathering of debris as it's basically being shot out of wherever it was, becoming projectiles? Why are these particles gathering like they are? And it was really interesting to follow this thread. I'm going to pull that up right now, and you guys can follow along. We'll have this link in the descriptions. But it's a great example of one of my favorite things in science, which is learning something new that you didn't learn before. And when you observe it, you say, oh, that's weird, or that's interesting. And so this thread from Dr. Phil Metzger, you can follow him online if you aren't already at Dr. Phil Till. That's DrPhilTill. And he goes through this. I'll talk about this, but I'll give his perspective of this, and then we can talk about it here at the end. So he says at the beginning, I'm shocked by the streamers in the ejecta. In ordinary granular splash experiments, we see nothing like this. A few musings about this in a thread. Physicists have done granular impact experiments where a steel ball, for example, is dropped into a sandbox. Here's an example. You can see the impact ejecta is in the shape of a cone, fairly uniform all the way around. And then he provides a source of that research. And he says, here's another example from a paper in Nature. Click to see full picture. These studied the rebound splash up the center line, but you can see the initial splashes are cones, fairly uniform in density all the way around. Streamers, like we see in the DART images, he says, which I find shocking, were first seen in the Hayabusa 2 impact, which we did an episode about. This was JAXA, the Japanese Aerospace Exploration Agency, and that actually brought back dust and debris from that asteroid in a capsule, and it returned to Earth, and we just got to see some actual results of what's inside. Surprise, they found water. But this was first seen in the Hayabusa 2 impact, and the image of that impact is annotated in red in this picture to show the arrangement of streamers. So in these cases, somehow the physics is causing the granular particles to form into lines as they flow out of the impact site. But how? He says granular material is not like water. Water has high surface tension, which helps it form into jets. Cool structures can form around impact splashes, including streamers, and he references this journal here. But granular materials have nothing like the strong surface tension of water. Yes, there is cohesion between particles, but it is super weak compared to impact dynamics and should be unable to organize massively sized streamers. Another reference there. He says one clue comes from looking at the moon. And the Tycho crater near the bottom of this picture has crater rays shooting out from it. See the lighter rays emanating from the crater? And we can see that here. Those were formed by streamers in the ejecta. Some went super long distances. And there have been a few recent papers motivated by the Hayabusa 2 imagery to explain the formation of streamers or patterns in the ejecta sheets. This is Cadono et al. That's 2022, Earth, Planets, and Space. There are 3 types of patterns that can form, including both streamers and meshes. So I will leave this up here for you to check out. But the general idea here is that we went into this thinking we would see a very evenly distributed cone of debris after the impact, and we did not see that. We saw something new and shocking that we still don't understand, that once we do, we can learn more about the physics of the reality in the solar system. Because one of the things that we do know is that things, especially particles, like to gather in space. Whatever that action is, they like to gather. And there seems to be something about that like there is here. My first thought here was maybe there's an amount of static electricity or just higher electron capacity because there's solar radiation. There's nothing to block it. So you're kind of just like charging the surface. And if there's distance between those particles for that energy to sit, that to me at a gut level seems like that makes sense. Kind of like, we gather static electricity from moving around. Maybe that friction of everything trying to get together, there's a certain amount of charge that as these particles release, there's a certain amount of them that stay together in these spindles. That's an idea. Again, I am just throwing an idea out there off of what right now makes sense to me. And if the Hayabusa 2 asteroid, this is another point, if the Hayabusa 2 asteroid had water on it, and we see that water can create these spindles, then is it possible that this ejecta had a lot of water, and that's why those spindles are happening, because there's a level of H2O particles that's binding together the dust, or creating a similar scenario where that dust now becomes more of a fluid and has a lot of the same effects and characteristics that water would have as it has those droplets. So I thought this DART mission was amazing and really cool to follow. It blew a lot of our minds. I got a lot of feedback from folks sharing it out there, how exciting it was. Most people had no idea that was happening, but it was a really exciting thing, and I felt that from you guys. So if you have any further questions about DART or any other questions, I'd love to put them on a future podcast. One of them that came up that I do want to address, because it is a good question, in the case that we're trying to defend the planet from an interplanetary impact. Kind of the movie scenario is nuke it. Just blow it up. Why not? If you have this big asteroid that is coming at you and you have these nuclear bombs, why not just use them? One thing is definitely, I don't think we know too much about how a nuclear bomb is going to work in the vacuum of space. Not 100% sure. And so taking that risk on the last chance to save humanity, if that's your only option, yeah, go for it. But let's say you're successful. Let's say you successfully detonate that asteroid. Especially in the case of Armageddon, right? They cheer when they blow up the asteroid in half. And yes, they saved Earth then. But that asteroid is going to come back. And all that debris is going to come back with it. And then they're going to have an even harder time dealing with the almost infinite amount of material that's going to be coming at them that could do damage across the whole planet. And that's my answer to why you don't want to just like toss a nuke at an asteroid. You really would have to think about what's going to happen after you hit it. Again, if you have no other choice, it just comes out that week. Yes, I agree. Send a friggin' nuke at that asteroid and we'll deal with it later. I get that. Maybe that'll spur some progress in orbital debris detection and planetary defense missions. There's a valid point to that. But the beautiful thing about the DART mission is that if we do understand where an asteroid is and if it becomes a potential threat to impacting the planet or the moon or any of our other planets in our solar system, if we can have a better idea of where this stuff is, and if we catch it early, we can send a small spacecraft that's launchable today, like the DART mission, which was launched on the Falcon 9. The physics means we only have to move it a tiny amount in order to change its final position, and that would reduce the potential of dealing with large debris that would happen. Clearly, there's a lot more debris from something like this than even I would have expected, and clearly all the planetary scientists expected. So it's a much cleaner, much more strategically placed nudge early on so that we don't need to just obliterate the crap out of it and create a giant asteroid belt that we have to go through and deal with every time it comes back around, right? So that's my thoughts on the DART mission. And again, send your questions in if you have any more about this type of stuff, asteroid impacts and saving the world.